I was supposed to give this lecture today through the internet, but unfortunately, due to reasons beyond my control, this is not possible, so I have resorted to the option of recording the talk here, and I hope that that this doesn't matter too much. And I'm going to be talking about geothermal energy, but with emphasis on geothermal energy in Iceland. So I'll talk about types and nature of geothermal energy, the use of geothermal energy in Iceland, and the environmental impact of geothermal energy compared to, for instance, fossil fuels. And I'll also address the question, is geothermal energy a sustainable energy source? But before we start on that, I want to address some basic concepts, just to make certain that everyone understands sort of the main concept relating to geothermal energy. In hydrology, we speak of the hydrological crossroads, and that refers to basically the routes that water can take once it has fallen as precipitation onto the surface. And this is of importance because eventually some of this precipitation becomes groundwater, and that groundwater eventually becomes geothermal water, given the right circumstances. So the water can flow along the surface and become surface runoff, or it can evaporate, and then thirdly it can infiltrate into the ground and become groundwater. The fourth possibility is, of course, if it falls as snow in highlands or on glaciers, it goes into storage, which eventually is released when the snow or ice melts. And what route is taken depends on many different factors. Rainfall intensity is important because each surface has a certain infiltration rate, and if the intensity of the rainfall exceeds that infiltration rate, the water will flow along the surface. Temperature is of importance. If the temperatures are high, then much of the precipitation will simply evaporate. But if they are low, then the water cannot evaporate. And you can see that, for instance, if you look at countries like Ireland and Iceland, wetlands are very common because these are cool environments, and water doesn't easily evaporate from the surface. Surface type is of importance, and if the surface is very compact, then we have low infiltration rates and therefore little groundwater, and even though we have heat underneath the surface, we won't have geothermal water because we need to get the water down there into contact with the heat source to heat it up. And this is a problem in many places, for instance in Iceland. Seismic activity is of importance here, because if we have seismic activity like we usually have in volcanically active areas, then the earthquakes actually fracture the bedrock, and this allows the water to infiltrate into the ground more easily. So seismic activity really rejuvenates geothermal systems. Slope is of importance. Of course, if the precipitation falls on flat ground, then it tends to, with time, seep into the ground, even though it's a compact surface. But if it falls onto a steep slope, it has the tendency to flow on the surface, even though the surface is porous and could actually accommodate all this water, but the slope simply, or rather the water takes the easy route. Once in the ground, we have basically two types of groundwater, we could say. Soil moisture, this is the water you find in the soil, typically in the uppermost part. It can extend some centimeters or even a few meters into the ground. This source of water is of great importance because most vegetation uses this water. Usually vegetation cannot access or get in contact with deep groundwater, so it uses soil moisture, and about 0.06% of all fresh water on the earth is of this type, and this is basically what sustains the flora. Temperature of this water reflects air temperature at a given time, so we have diurnal variations. This water is cool in the night and warm in the day. And then if we go further down, we get what we call true groundwater. This is water that fills all cavities in the ground down to depths of about 4,000 meters. And about 24% of all fresh water on Earth is stored as groundwater. The upper limit of the groundwater is called the groundwater table, and usually, well, always, groundwater temperature reflects the mean annual temperature of the area in question. In summertime, the water that falls on the surface and seeps down is warm. In wintertime, it's cold, and then it mixes, of course, in the ground, and basically the temperature becomes the same as the mean or average temperature of the area in question. Now, geothermal water or geothermal groundwater is any water that has a greater than normal temperature due to contact with underground heat source. Here in Iceland, for instance, in the lowland areas in the south and west and east, the mean annual temperature is about 4 degrees. So through groundwater, if we pump it up, it should be between 4 to 5 degrees. If we get water that's warmer than that, say 10 degrees or 15 degrees, this water has come into contact with some heat source in the ground. So we can simply say that geothermal water is heated groundwater. Another concept which is of importance is the geothermal gradient. As you may or may not know, the core of the Earth is very hot. It's about 6,000 to 7,000 degrees centigrade. So it's logical to assume that as you go down into the ground, the temperature should increase with depth. And it does. On the continents, for instance, like on the Canadian Shield in Europe, in the United States, in South America, typically, well, in certain areas in South America, typically at depths of 1,000 meters, the temperature is about 30 degrees centigrade. Here in Iceland, we have 3 different regions when it comes to the geothermal gradient. Outside of the volcanic zones, the temperature is between 50 to 100 degrees at depths of 1,000 meters. This is higher than you would see in the continents, of course. In fact, in some cases, more than 3 times higher. We have also some areas that are outside of the volcanic zones, but are in connection with old extinct volcanoes, where we get temperatures between 80 and 150 degrees. Now, within the volcanic zone, it can be close to boiling at the surface, and the temperature increase can be as high as 1 degree for every meter you go down. Now, when groundwater comes into contact with molten or hot rock, it heats up, and the low density hot water rises to the surface and forms hot springs. And these areas are called hot spring areas. It's not just the temperature that's different. If you compare hot spring water to groundwater, it's also the amount of dissolved materials. Typically in groundwater here in Iceland we have about 50 to 60 milligrams of dissolved salts or materials in a liter. When we are dealing with hot spring water, we can have these values are much higher. They can be 500 milligrams per liter, and in near active volcanoes it can be as high as 2,000-3,000 milligrams per liter. And this is simply due to the fact that hot water dissolves materials easier than cold water. So here is a diagram showing how a typical hot spring area forms. We have precipitation taking place. This water infiltrates the ground through cracks and fissures and goes down, and here is a hot or molten intrusion. The water gets into contact with this and heats up and rises as hot water, and of course following cracks and crevices up to the surface, where we have the surface expression is of course the hot spring area. We divide hot spring areas in Iceland into two categories. The high temperature hot spring areas, these are always found within the volcanic zone, and they are always in connection with active volcanoes. Temperature at depths of 1000 meters is about 200 degrees or more, up to 800 degrees. So this is superheated water, and if we pump it up to the surface it turns into steam basically. There are very high concentrations of dissolved materials in this water. We can see up to 1500, or rather more than 1500 milligrams per liter. And if you want to use this water, for instance, for space heating, it's not possible to pump this directly into the houses, because it would fill up the pipes within weeks, as this material would fall out of the water. So usually we use heat exchangers. We pump up cold water and hot and this superheated water, and within the heat exchanger the heat is actually transferred from the hot water over to the cold water, which is then pumped into the houses. The steam can also be used to generate electricity, to drive turbines that basically produce electricity. And then we have the low temperature areas. These are mostly outside of the volcanic zones. They are usually in connection with extinct volcanoes, not necessarily always. Temperature at 1000 meters is always less than 150 degrees. The amount of dissolved materials is much lower, 200 to 600 milligrams per liter, and therefore we can pump this directly into the houses. And the first areas that we started using in 1940, when we built the Reykjavik geothermal power plant, we were using low temperature areas within the city. There are boreholes, 20 boreholes within the city limits, where we pump this water up and pump it directly into the houses, and we use it to heat them up. Of course, this water is not suitable to generate electricity, because we don't have the steam. Now, these low temperature geothermal areas are we have about 250 of them in Iceland. The total flow is estimated to be about 2000 liters per second, and 2/3 of this water is flowing from areas within the west of Iceland. The high temperature areas, we know of 28, but some of them are not accessible. They are under glaciers. The total area of these is about 550 square kilometers, but they vary very greatly in size. The smallest high temperature geothermal area in Iceland, Hveravellir, is about 1 square kilometer, while the biggest one, Torfajökull, which is a glacier actually, is about 140 square kilometers. And here we have a map showing geothermal areas in Iceland. We have the black dots here showing low temperature geothermal areas, the blue ones high temperature geothermal areas, and the shaded areas here are the volcanically active zone. That means that within these areas we have actually active volcanoes that erupt. And here the arrow, where the arrow is at this time, we actually have an ongoing eruption which started on August 23rd and is still going strong. Well, actually, it's a little bit further to the left. It's here where we have the big blue dot. Now, 60% of energy consumption in Iceland comes from geothermal energy. We have about 60 large geothermal plants that provide water for space heating. That means for heating houses, swimming pools, snowmelt, greenhouses, and so on. And we have 5 large power plants that use geothermal steam to produce electricity. About 90% of all houses in Iceland are heated with geothermal energy. The one I'm sitting in now included. Here is a diagram showing how you can use geothermal steam to generate electricity. You have a borehole. This is a closed system because this is superheated water, and if this system wouldn't be closed, then this would simply turn into steam. And basically the process involves taking this water, cooling it, or lowering the pressure a little bit, separating the water from, then we get some steam, and the water is separated from the steam, and then the steam is used actually to turn the turbine, which produces electricity, and then it's then used further. It's basically blended with the water that we use for space heating. Nothing goes to waste within the system. So in 2014, if you look at geothermal energy, 59% of it was used for space heating. We used about 18% of it to produce electricity. Fish farming used 6%, industry 6%, swimming pools 4%. Swimming pools in Iceland are a little bit like Tim Hortons in Canada. We have one on every corner, and simply due to the fact that we have easy access to cheap warm water. Snowmelt, we have snowmelt systems in pavements and roads, and that uses about 4% of all geothermal energy here. And then greenhouse is 3%. We produce most of the tomatoes, cucumbers, red and green peppers, and so on that are basically consumed in Iceland. They're grown in these greenhouses. So if you look at the total energy use in Iceland, hydropower is about 20%, and most of it are glacial rivers, which have a huge annual variation in flow. So you need to build large reservoirs to regulate the flow, and therefore drowned very important areas in the highlands. So these projects are very controversial, and there has been more emphasis in the last years to use geothermal power to produce electricity. The environmental impact of those power stations is far less than of the hydropower stations. Oil, 25%. Most of it is oil used for our fishing fleet. 1/3 of our income comes from fishing, and the fish is caught by very large trawlers that use huge amounts of energy. So the Icelandic economy is actually quite sensitive to oil prices, even though it's only 25% of our energy use, because basically the profit we make from fishing is the price minus the cost, and as the oil prices go up, then the cost goes up, and then we are making less from our fishing. One of the ideas is to use geothermal power to generate hydrogen, and use hydrogen for our fishing fleets, and then we could be basically, we wouldn't have to rely on any or very limited oil imports. Now, what are the environmental impacts of geothermal energy? It is definitely environmentally friendly if we compare it to other sources of energy, like fossil fuels. Producing 1 unit of energy with geothermal energy produces 1% of the pollution that would occur if you would produce the same amount of energy using fossil fuels. But geothermal power plants can have a huge local impact, and I'm going to talk a little bit more on that, about that. There's the visual impact. Many of these hot spring areas or geothermal areas are within the most beautiful parts of the island, within parks and so on, and they are a big eyesore. You're traveling basically through unspoiled landscape, and then you come across a big power plant. Large steam columns often rise from these areas, which obstruct the view, and pipelines, borehole domes scar the landscape, as do the power plants themselves. And then, of course, you need power lines. It's not just the pipelines, it's also the power lines that go from the power stations to the towns and cities. So these cause objectionable visual effects. But the important thing here is all of these are easily reversible, which is not the case with, for instance, reservoirs associated with hydropower stations. So if future generations don't really want these things, they want to reclaim this landscape, they can simply plug the boreholes, remove the structures, and basically recover these areas very easily. We also have noise pollution associated with boreholes. If you're close to a borehole that's blowing, it's like standing next to a jet engine, so that's another factor. Even though the gases that we release do not have global effect, it's not affecting, for instance, climate. There are poisonous effects. Most of these gases are, well, to a large extent it's carbon dioxide, but also sulfur dioxides, and these are poisonous to flora and fauna. And we have also studies show that they affect human health also. But there are ongoing experiments to pump these gases back into the ground, and then and hence reduce this negative effect of the geothermal power plants. But then again, we have discussions on what effects that will have on groundwater that we use, for instance, for drinking. How deep do we need to pump this down? We also have noticed that pumping this water down has increased seismic activity, and so on and so forth. Now, the big question is geothermal energy renewable? And the correct answer to this question is yes and no. We will have geothermal energy in Iceland while we have active volcanoes, probably for the next at least 1 to 10 million years. But each geothermal system has a certain capacity. We can look at the system as a tank, and there's an inflow into the tank, And if we exceed that, if the water that we pump from the system exceeds that inflow, if we exceed the capacity of the system, we drain it. The tank will basically, the level in the tank will go down until it empties. And this system then needs a huge amount of time to basically recover. However, if we stay below the capacity of the system, this system can stay usable for many, many generations, and possibly forever if we basically rest the area every now and then. So I hope this tells you a little bit about geothermal energy in Iceland and how we use it. You're welcome to email questions to me, and I'll try to answer them the best I can. My email address is kag@hive.is. Thank you very much.